I'm Martin Lindsay from the Study and Learning Centre at RMIT University. This is a short movie on surds. A surd is a number that cannot be written as a fraction. For instance, numbers like root 2 and root 7 have got a series of decimal places after the decimal point if you type those into the calculator, so you can't write those as fractions. Numbers that are not surds are written below. You can see that 2 can be written as a fraction 2 over 1, 1.3 can be written as 13 over 10, and root 4, which is 2, can be written as 2 over 1. In other words, they can all be expressed as fractions. The trick in simplifying surds is to look for square factors. Here are a number of square factors: 4, which is 2 squared, 9, which is 3 squared, and so on up to 100, which is 10 squared. Look at this example. We have the square root of 200, and what we do is we express it so that there's a square factor under the square root sign, which in this case is 100, shown in red. 100 times 2 under the square root sign is the same as the square root of 100 times the square root of 2. Notice the square root of 100 is 10, so our answer is 10 root 2. Notice also the square root sign is sometimes called the radical. Similarly, 3 root 48. 48 is not a square factor, but 16 times 3 is, which gives us 3, the square root of 16 times 3. The root 16 is 4, and root 3 is left on its own. In other words, we now have two whole numbers, 3 and 4, which gives us 12 root 3. So our answer is 12 root 3. When it comes to adding and subtracting surds, one has to be mindful of the fact that only like surds can be added or subtracted. For instance, here's a question: 8 root 5 minus 3 root 5. The root 5s are the same in both terms. In other words, we can subtract these two terms. 8 root 5 minus 3 root 5 is 5 root 5. However, if we have this question where we have 2 root 3 plus 5 root 7 minus 10 root 3, notice there are two different surds here, a root 3 and a root 7. So we have to keep those separate in our answer. So that gives us 5 root 7 minus 8 root 3. Here's the rule for multiplying surds, and it's probably easier to illustrate this with an example. For instance, root 3 times root 2, we can place both the root 3 and the root 2 under one square root sign. In other words, that becomes the square root of 3 times 2. 3 times 2 is 6, so the answer is root 6. Second example, we have 3 root 5 times 4 root 7. 3 and 4 are the whole numbers, so you multiply those two separately, whereas the root 5 and the root 7 can go under one square root sign, the square root of 5 times 7. So that gives us an answer of 12 root 35. Finally, here's another one. We start with 2 root 10 times 7 root 6, which gives us initially 14 times the square root of 10 root 6, which is root 60. But when you get a large square root sign in particular, see if it will simplify into something a bit smaller. In other words, look for a square factor, which in this case is 4. In other words, root 60 is the square root of 4 times 15. 4 times root 15, the square root of, gives us 2 times root 15. So we now have 4 times 2, which is 28, root 15. In dividing surds, we use a similar idea. And again, let's look at the example here. Root 18 divided by root 6 is the same as the square root of 18 divided by 6, which is 3. In other words, our answer is root 3. Here's a number 4 divided by a surd, root 2. So here we have 4, which can be expressed as root 16 divided by root 2. Notice I've expressed both numerator and denominator as surds, because we can now use the rule, which is the square root of 16 divided by 2, which is root 8, And again, notice that this simplifies because we can use a square factor here of 4. So root 4 times 2 is 2 root 2. Rationalizing a surd is a way of simplifying an expression where the surd is on the denominator. For instance, if we have 2 over root 5, notice the surd is in the denominator here. And to simplify that, we can multiply 2 over root 5 by root 5 over root 5, which is effectively 1. In other words, 2 over root 5 times root 5 over root 5 is 2 root 5, multiplying the top line. Root 5 times root 5 is root 25, which is 5. Notice the answer, 2 root 5 over 5, has got no surd in the denominator. Similarly, here we have surds top and bottom, but the purpose here is to try and get rid of the root 2 in the denominator. So we do as before by multiplying both top and bottom by root 2 over root 2, which gives us root 10 on the top. Root 2 times root 2 on the bottom is 2 times 3, which gives us 6 on the bottom. Again, notice in both examples here that there are no surds in the denominator. That's rationalizing surds. Conjugate surds are just a slight extension of the rationalizing surds problem we were doing in the previous slide. Here's an example, root 3 over 5 plus root 2. What we do is we look at the denominator and then we write the conjugate of that, meaning we write the same terms, 5 and root 2, but with a negative sign between them. In other words, we're multiplying by 5 minus root 2 over 5 minus root 2. Now we multiply out the problem. This gives us root 3 brackets 5 minus root 2 over 5 plus root 2 multiplied by 5 minus root 2. If we multiply out the bottom line, we'll get 4 terms. But notice in particular that when we multiply out this bottom line, there'll be the surds that will cancel out. In other words, we'll have no surd left in the denominator. So our answer is 5 root 3 minus root 6 divided by 23. Always make sure that the answer does not have a surd. Now try some problems for yourself. The answers to these questions are on the next slide. Thanks for watching this short movie.